All right, so now what we're going to do is we're going to really look at a graphical interpretation of this process that we started like this, and then we can continue it like this. And I went all the way up to x equals 2, and I got what we're going to see is a pretty good estimate for f of 1, but not very good estimate for y of 2 at all. So let's just sort of look at graphically what's going on. So what I'm doing is I'm starting with the point 0, 2, and I'm plotting that point, 0, 2. All right, and then what I'm doing is I'm using the slope from that point to calculate another point. And the next point I got was 0.2, 2.0, because the slope was horizontal there. All right, and then my next point that I got from that, using the point 0.22, is I got the point 0.4, 1.96. So this is scaled by 0.2s. So 0.4, 1.96, here's 1.8, 1.96, about there. All right, and then but each time I'm using the slope from the last point that I computed to compute the next point. So I'm using this point to compute the next point. The next point is 0.8, 1.75. So 0.8, 1 point, here's 1.6, 1.75 is about there. All right, but because I used this point, which I knew, to compute this point, but this point was only an estimate. In fact, I doubt that that's correct. And then I used this point to estimate that point. So then now I've compounded the error. And then I use this point to estimate that point. So at every step that I do this, I compound the error and increase the amount of error that I'm finding at each step. So if I want to go and plot all these points, then the graph that I get looks like this. All right, and I see like this nice smooth curve happening here, and then it sort of goes berserk over here. These seem to look a little bit unstable. All right, so the next thing I said is, okay, we can print out a slope field of this. So we have, right, this is our equation, dy dx equals negative 2x over y. All right, that's what dy dx, I put f of x there, but that's because I was just thinking of writing this a different way. So dy dx equals negative 2x over y. That's our differential equation that we're solving. So we can produce a slope field for that. So I use technology to produce this slope field. I have said in the past I don't usually do that. I don't find it very useful in this case. This is tremendously useful. I just Googled, Desmos. This is a Desmos graph. Desmos slope field, and there are like 2 or 3 different apps that do it. Some are good, some are bad. All right, so here's what the slope field looks like. So what if I take these points and put them on this slope field? Well, it looks like this. All right, and what you can see here is that we start out following the slope field pretty nicely. Like if I were to just sketch my own solution through that initial condition, this is pretty much how it would draw. It follows pretty nicely all the way. All right, so everything from here to here looks pretty nice. And then over here, it starts to go crazy. All right, so something blows up over there. So one of the things that we can notice is the slopes here are starting to get vertical. So dy dx is becoming undefined. So as we get closer and closer to x equals 2, in fact, which is where the truly vertical tangent is, as we will see, the method starts to really go haywire because it can't handle that dy dx that's undefined. So that's an interesting thing to see. But as we're going along here, we see a pretty decent curve. Now, what else can you do? You can solve this equation analytically pretty easily. Now, remember, the advantage of this method is it's useful for equations that you cannot solve analytically, which there are a lot of. I picked this one because we can solve it analytically, and then we can compare that analytical solution to what we get. So this is not too hard to do. I'm going to bring the y dy over here. I'm going to leave the negative sign over there. I could have bring the negative over, but I think it'll be a little more efficient to do it this way. Then I'm going to integrate both sides. So I'm going to have y squared over 2 equals negative x squared plus c. I'll bring the x squared over, so I have y squared over 2 plus x squared equals c. Now we'll use the initial condition 0, 2. So x is 0, y is 2. I plug that into here. 2 squared over 2 plus 0 squared equals c. It's pretty easy to get c equals 2. Therefore, our particular solution is y squared over 2. I'm going to put the x squared in front. X squared plus y squared over 2 equals 2. Now, if you've studied conic sections at all, you know that that's an ellipse. And we can also just plug that function. One of the nice things about Desmos is that it can graph a function without solving for the variable. So I put that into Desmos and the slope field, and I got that. See how it's a nice ellipse? Now that's the ellipse is the real solution, if you will, the real solution to this differential equation. The real solution is this ellipse. Now, the solution that we got, the solution points that we got, you see they follow it along pretty nicely as long as you don't stray too far from the initial point. But the farther you stray from the initial point, the farther off you get. So let's come back to the idea that we could use the Euler's method to estimate something like y of 1. So by using this method, and if I just keep computing until I get my x value up to 1, I'm going to get 1.57 as a point. So I'm saying y of 1 is approximately 1.57. Well, is it? If we look at the graph of the solution, here's 1, and what's our point here? Well, it looks like it's 1.2, 1.4. It's maybe like 1.41. So our solution is pretty far off. So one of the reasons is we've chosen a fairly large delta x of 0.2. So if you were doing, a mathematical computing, probably the largest delta x you would ever pick is 0.01, and you would probably use something like 0.001. All right, but so this is what's going on. This is our analytic solution, our numerical solution, our a graphical version of our analytic solution, and a graphical version of our numerical solution. So you can see that it's an approximating technique. It gets worse the more points you use. There are more sophisticated techniques. You can look up something called Runge-Kutta method. That's one of them, and that will adjust as you go along and use the second derivative as not just the first derivative. You can also use smaller values for delta x, and you can get much more accurate solutions. Okay, but this is basically the process which we will now just look at an example of solving a problem with.